So this question reads, the drawing shows two situations in which charges are placed on the X and the Y axis. They are all located at the same distance of 6.1 centimeters from the origin O. This is the origin here. For each of the situations in the drawing, determine the magnitude of the net electric field at the origin. For each of the situations in the drawing, determine the magnitude of the net electric field at the origin. So as usual, let's begin by explaining the principle of everything that is taking place here. If you look at this question, it's just based on what we call electric field due to multiple point charges. That's why I'm noticing to say we don't have one, two charges. We have all three, which gives us um, multiple point charges, all these point charges. And they've told us to say they are all located at the same distance of 6.1 centimeters from this origin O. So we have that one, we have that one, and we have this one. What are we going to notice? Each of these charges that we have here are going to create their own electric field at the origin. This is the origin. Each of these charges are going to create an electric field at the origin here. So how do we calculate the net electric field if there are those multiple fields? We get the vector sum of all the individual electric fields. As simple as that. So we're also going to be introducing the concept of vectors. I'm sure you remember everything that we did when we were doing vectors. It's the same concept that we're going to apply here. In order for us to get the total electric field at the center or the net electric field at the center O, we're going to find the vector sum of these individual charges from our multiple point charges, just like that. So how do we calculate electric field due to a point charge? How do we calculate electric field due to a point charge? We say electric field is equal to what? It's equal to K, which is a Coulomb constant, Q over R squared, like this. I've already said K is the Coulomb constant. Then we have Q, which is the magnitude of the point charge itself, and R is the distance, the radius from the point that we are referring to. In this particular case, it's from the origin. R is the distance, like that. But since it's point charges and electric fields, we know to say they always carry directions, which means we are also supposed to follow the directions. And we are also, in case we are given different charges, I'm sure you've already looked at this, but I'll just repeat it. The rules. What rules do we follow in directing an electric field? When we have a positive point charge, that means the field points away from that particular charge. So in this particular case, we have this one, which is positive. That means the field always point away from that particular charge. Then if we have a negative field like this one and that one, we know to say the field always points towards the point charge itself. Those are some of the things that you're supposed to know because the electric field always has a direction. Then in order for us to find the net charge, you just say this will be equal to square root of EX squared plus EY squared, which means the summation of our fields in the two different axes that we've been given. For example, in this particular case, they've given us the positive, I mean the X and the Y axis, like that. Okay, so the first thing that we're going to do is to calculate the electric field from each charge. How do we do that? First, let's convert our distance from centimeters into meters. So if I divide this by 100, what distance am I going to get? Our R will be, what will be the value of our R? Will be 0.061. 0.061 meters. That will be our R. Then if you look at the charges themselves, I've talked about it to say if it is positive, the field is going to point away from it. So I'll just draw a diagram so that you don't forget about it. For example, from this one, that means the field is going to point in that direction, like that. Then from this one, Then we also have 1 from this one, since we're using the center as a reference. We're using a center as a reference like that. Okay. So that means our electric field is going to point in that direction from the positive one, then in that direction from the negative, and in that direction from the positive. I mean, from the negative again, it's pointing towards them. So, which means here it's pointing towards the positive y-axis. Here it's pointing towards the positive x-axis. Even this one is pointing towards the positive x-axis like that. So that is what we are basically going to do. But even the charges themselves, they've been given in micro coulombs. We have to convert them into coulombs. How do we do that? We know to say micro and the coulomb. What is the relationship? What's the relationship between, or the conversion factor between a microcoulomb and a coulomb? Yeah, so I'm sure we remember to say we multiply it to an exponent of -3. So we're going to say this is going to be equal to -5 times 10 to the power minus 6 coulombs. This is micro, so it's minus 6. Then even this one, it will be -3 times 10 to the power minus 6 coulombs. Then that one, it will be positive 2 times 10 to the power minus 6 coulombs, like that. And that is what we're going to use. Then in our formula, there is K, which is the coulombs constant, and this one is 8.99 times 10 to the power 9, like that. That is the value of our coulombs constant. So in most cases, since it's 8.99, we just use 9 times 10 to the power 9. That is the one that is used mostly. And this one is actually very easy to remember. So let's find E1. Let's find E1. Our first charge is this one, the positive one. So we're going to say this is equal to what? It's equal to K, which is 8.99, or let me just use 9. 9 times 10 to the power 9 multiplied by the magnitude of the charge, of the point charge itself, which is 2 times 10 to the power minus 6, divided by the distance squared. The distance is 0.061 squared, like that. And this is going to be equal to what? I can plug it just the way it is in my calculator. I can plug it just the way it is on my calculator. It's giving me 4.84 times 10 to the power 6 newtons per coulomb. That is the first charge, which is this one. Let's go to E2. E2, we are going to consider this one, which is also on the x-axis. So this one, we're going to apply the same formula to say 9 times 10 to the power 9, like that, in brackets. And if you look at this formula, we have these absolute signs here. What does that mean? That means we will not consider the negative. So even here, if I say multiplied by -3 times 10 to the power minus 6, like that, it will the just by you introducing the absolute signs, it deals away with the negative here, which means your answer is supposed to be positive inside the absolute sign. There, divided by 0.061, again squared, like that. Okay, I can punch it the way it is, just ignoring the negative on my calculator. 9.0 times 10 to the power 9 multiplied by 3 times 10 to the power minus 6 divided by 0.061 squared. 0.061 squared. This is giving me 7.26 times 10 to the power 6 newtons per coulomb. That is my E2. And let's go to our E3, which is from the 5. This one is in the y-axis, so we're going to do the same. 9 times 10 to the power 9 multiplied by the absolute signs of -5, which will just give us 5 itself. 5 times 10 to the power minus 6 coulombs divided by 0.061 squared, like that. If I plug this onto my calculator, I'm getting 1.21 times 10 to the power 6. 1.21 times 10 to the power 7, sorry, newtons per coulomb. That is my E3. So these are the uh, fields due to each point charge. Now, what are we going to do? Let's use let's find the vector sum of all these. We know to say this one is the x-axis, it is in the y-axis. These two are in the x-axis, and they're both pointing towards the positive x direction, which means they're both positive. Whilst this one is also positive since it's pointing towards the positive y direction. It's pointing towards the -5 there. So that's what I'm going to do next, which means this summation of my fields in the x will be equal to what? What will be my summation of the fields in the x-axis? Summation of the fields in the x-axis. It'll just be E1 plus E2, right? So I'm going to say 4.84 times 10 to the power 6 plus 7.26 times 10 to the power 6. How much is this going to give me? It's giving me 1.21 times 10 to the power 7 newtons per coulomb. This is in the x-axis. Then in the y-axis, we're just going to get the same one. 1.21 times 10 to the power 7 newtons per coulomb, like this. This is what I have in my y-axis. Then for me to find the net electric field, I'm going to say this will be equal to summation of the x, so which is 1.21 times 10 to the power 7 squared plus 1.21 times 10 to the power 7, also here squared. This is going to give me how much? What answer are we going to get there? Anyone? Okay, so if I plug it into my calculator the way it is, it's giving me the final answer of the net electric field on the center, which is the origin, being equal to 1.71 times 10 to the power 7 newtons per coulomb. That is the net electric charge. Can even put it in black. That is the net electric charge. Is there anyone with a question here? Any question? All right, so if there's no question, then we can move on to the next one.